We're going to take a look at this concept of a conjugate. Now this is quite important in complex numbers, especially in proofs. So we're going to have a look at some properties of conjugates and also how to do a proof question. So a conjugate simply is a complex number with the imaginary part negated. Okay, so if your complex number is z plus bi, then the conjugate, written with a star in the corner, is written as a minus bi. Okay, so let's think about what that looks like on the Cartesian plane. Sorry, what it looks like on the complex plane. Okay, so this is the real part and this is the imaginary part. So a plus bi, let's just draw it in this first quadrant right there. Okay, so this is a, this is b. A minus bi, alright, I hope you know that it's just a pure reflection. Okay, so same distance down here. Alright, so that's still a, and this is the negative b part. Alright, that's easy. The conjugate of a complex number is simply the reflection of this over the x-axis. Okay, so it's just down there. Alright, so that means if your complex number was in the second quadrant, then the conjugate will be down here. If the complex number was down here, then the conjugate will be up there. Okay, so what's the point in doing this? Alright, let's have a look at some properties of conjugates. So what happens if you multiply z with its conjugate? Alright, so this is leading on to this idea of proof. In the IB, sometimes, in the IB exam, sometimes you need to write a proof. So with a proof, where they don't tell you what z represents, you can just let it equal a general complex number, like a plus bi. So let z equal a plus bi, where a and b, if you really want to write this, you can also write this. Okay, a and b are real values. I know this seems a bit strange to write real next to an imaginary value, but just think about it, that makes sense. So when I do z times z star, and I'm just using a dot as multiplication, you don't actually have to show anything, you can just write next to it. It will be a plus bi times a minus bi. Now, when you expand these, you'll get your expression. Okay, so a times a gives you a squared, and hopefully you can see it's a difference of two squares. So all I need to do now is subtract the b squared I squared, and just remember I squared by definition is -1. Okay, because remember the definition of I is the square root of -1. Okay, so I squared must be -1. So this subtraction turns into a plus. A squared plus b squared. Hang on a second, this looks familiar. A squared plus b squared, that resembles something we've looked at before. It's the modulus, isn't it? But without the square root symbol. So it's the square of the modulus. This is strange. So z times z star is equal to the square of the modulus. Okay, so that is a property that is useful to know. In fact, for some proofs, they'll require you to see that. Okay, so you do need to know this. Now, here's another property you'll notice with conjugates as well. It deals with fractions. Okay, so what does 1 over z equal. So you might think, okay, I can write this as a power. You might think, okay, I can write it like to the power of -1. At the moment, we don't actually know how to do powers of complex numbers. Later, you will learn how to do this using de Moivre's theorem, which utilizes polar form. So at the moment, we're just sticking with our Cartesian form. So yeah, we're just simply going to do something similar to the previous proof. What happens here? So you can try this along with me. Let z equal a plus bi. So now we're just going to write 1 over a plus bi. Okay, nothing interesting. However, do note that this fraction has a complex value underneath, and it has an imaginary part. We don't like that. So we're going to do something to fix this up. We're going to multiply by its conjugate. Okay, so this is where the conjugate part comes from, is useful. So now we're going to do this. We're going to, just going to get a different color pen, multiply by a minus bi on a minus bi. I'm not sure if you know why I chose to do that. Right, so firstly, this is equal to 1, so I'm not really changing the expression. But if you look at the bottom part, can you see I'm going to have a difference of 2 squares? Alright, so let's follow through with this, and hopefully you'll see the magic appear. So in the numerator, you're going to get a minus bi. On the bottom, it's going to be a plus bi times a minus bi. So really it's z times z star, which you can already see the expression over here. Okay, so this is a minus bi. And then down here, I've got a squared plus b squared. So if I want to write this using the z notation, I can call the top part the conjugate of z, and then at the bottom I can call this the square of the modulus. Alright, so what did I find? Therefore 1 over z equals the conjugate divided by the square of the modulus. Just give you a moment to have a look at these two expressions carefully. Do you notice anything similar between the two? Yeah, actually the one that we just worked out is identical to the one on the left if you just rearrange it. You see that? So if I divide this by the modulus squared, and then I put the z on the right hand side, then I'll just get that. So this notation here, later on, like I told you, will be written as a power. You can link the reciprocal, can I say that? The reciprocal of a complex number to its conjugate and its modulus. Alright, let's now have a look at a proof question. In your textbook, it has a summary of some properties that they'd like you to go through after you've done some exercises. In section 14b, okay, you can see there that the modulus of a conjugate is the same as the modulus of the complex number itself. I think that's easy to understand because when you work out the modulus, you're squaring the real and the imaginary part, a squared plus b squared. It doesn't matter if b was negative, it gets squared. So that's easy to understand. This is the property that we worked out before. Now these two, probably not easy to see, We actually will come to that again when we do multiplication and division of complex numbers. And then lastly, hopefully you can understand this is an extension of the third dot point, all right? Because if you multiply z1 and z2, you now get a new result. Then you consequently multiply by another complex number, say z3. Then you're just renaming that result as z1 and then z3 as z2. And then you get a new result, and then you just so on and multiply. Looks like this question could be an induction question. We have to practice some induction. Okay, so now we're going to have a look at a proof question. I just saw one here. Question 12, exercise 14b. I'm just going to quickly write this up, and we'll give it a go. So we're trying to find something that satisfies 50 over z star minus 10 over z equals 2 plus 9i. Given that you know the modulus of z equals 2 root 10. Now there are a couple of ways to approach this. Yep. So you could let z equals a plus bi, and then we can equate components. Let's give that a go, but you should find that using the properties of the z is actually going to be a whole lot easier to work this question out. Okay, so let's do method 1. This is probably the harder way to do it. So I'm going to let z equal a plus bi. Just remember the question is asking you to find what the z is. So I'll just remind you, it says find the complex number z. Yep. So when I write like that, now I can substitute into my expression on the left hand side. I've got 50 over a minus bi minus 10 over a plus bi. The right hand side is 2 plus 9i. I'm not going to do anything to it. Okay, so to resolve the denominators, I have to have common denominators. So I have to multiply this by a plus bi. And this right hand side, 10 a minus bi. It's all over a minus bi over a plus bi. Right hand side doesn't change. Okay, keep going. So 50a minus 10a is 40a. 50b plus 10b is 60b. 60bi. The bottom part is going to be a squared plus b squared. 2 plus 9i. Now I'm going to deliberately split this into real and imaginary part so you can see it clearly. So the the real part is here. Okay, so it's 40a over a squared plus b squared plus, and then we've got the imaginary part. So that's 60b over a squared plus b squared I equals 2 plus 9i. So what I'm trying to tell you is this term here on the left should be the same as 2, and then this term here on the right hand side here should be the same as 9. This is called equating components. Okay, so equating the real components. Okay, what do you get? You're going to get 40a over a squared plus b squared equals 2. I'm just going to write that as 40a equals 2a squared plus 2b squared. Alright, I'll just leave it at that and call that equation 1. Actually, I should divide everything by 2. Let me rewrite that one more time. So I'm going to get 20a equals a squared plus b squared. Okay, call that equation 1. Alright, so I keep going, And you can see here, because a and b are unknown, and I have two equations, I'm going to have simultaneous equations. Okay, so equating, where have I got it? Equating the imaginary components. I'm going to get 60b over a squared plus b squared equals 9. 60b equals 9a squared plus 9b squared. Divide both sides by 3. 20b equals 3a squared plus 3b squared. This is equation 2. Okay, so I could substitute one into the other to get the a and the b value, but okay, I haven't used the information says here, given modulus of z equals 2 root 10. Let's just see what happens though if we don't use it, because we should be able to continue on with this question here. So I can figure out a relationship. You notice a squared plus b squared in both, okay? A squared plus b squared in the first one. Oh, sorry, it was over here. I'm looking at the wrong part. Equals 20a. But over here, you got 3 of them. So I'm going to multiply that by 3, and that should equal 20b. I've just done substitution in a really strange way, okay? So I've just used 20a over here. There's 3 of them. Hope you can understand that. So now I've got 60a equals 20b. So divide both sides by 20. I've got 3a equals b. So b equals 3a. That means I can substitute this into one of the expressions and I can figure out what a is going to be. So we'll call that 3. Put 3 into 1. Okay, so 20a equals a squared plus, and b squared is 3a all squared. 20a equals a squared plus 9a squared. 20a equals 10a squared. 2a equals a squared. A squared minus 2a. Okay, factorize. So a could equal 0 or a could equal 2. Now a equals 0 is not going to be a sensible solution. If a equals 0, that means b would also equal 0, and then that would be nonsense because my original equation means I'd be dividing by 0. So that means a has to equal 2, which therefore b must equal 6. Now that given information they gave at the beginning of the question wasn't even used, but we'll just use that to double check if our solution makes sense. Alright, so the modulus of z should be square root of 2 squared plus 6 squared, which is 4 plus 36, which is root 40. Yep, and it's 2 root 10. Okay, so we did it the really long way. So what happens when you use the properties of complex numbers to figure this one out? There's got to be a shorter process, and that's right. Okay, so I'll just try to cover this up a little bit. Let's try this again. So we'll have a method 2, and you probably realize it already because you saw the multiplication process before. You'll see some things simplify, okay? So let's start again. We're going to go 50 over z star minus 10 over z equals 2 plus 9i. So we need to multiply that by z, so we've got 50z. This by z star all over z star and z, 2 plus 9i. Okay, so don't change that right hand side just yet. Now remember the property z star over z. So we've got 50 z minus 10 z star. This is the modulus of z squared equals 2 plus 9i. Okay, now I can bring in that modulus of z. Alright, so modulus of z squared equals 2 root 10 all squared. So 50z minus 10 z star, 2 root 10 all squared, 2 plus 9i. Okay, I'm going to square that out. So I'm going to get 4 times 10, 40. Okay, I'm going to bring that 40 to the right hand side. Actually, kill off all the zeros. Okay, so I'll multiply that by 4. So I've got 5z minus z star is 8 plus 36i. Okay, so now we need some way to factorize these two. If only they could have something common between the two of them, that would be great. Trying to think here. Z star would be related to the modulus of z squared. Okay, I'm trying to avoid doing that because in the previous slide we looked at, we noticed that z star equals the square of the modulus over z. So if I substitute that into it, I'm just going to end up getting a z squared. No, I think at this point it'll be easier to now substitute the a plus bi. Okay, so now I've got 5 a plus bi minus a minus bi equals 8 plus 36i. Okay, so now I've got 5a minus a, which is 4a, and I've got 5b plus b, which is 6bi, 6bi equals 8 plus 36i. So looking at that, I think you can easily see with the real terms, you got 4a equals 8, so a equals 2. And then from the imaginary terms, you've got 6b equals 36, so b must equal 6. Okay, so therefore the complex number must be 2 plus 6i. I didn't summarize the previous one. You can see the working over here. Now, obviously, this is the better way to do it, and I would suggest you utilize some properties to help simplify your calculations. So that was an example of using the conjugate as a way of solving a proof question, but more importantly, the properties of conjugates. Okay, you should identify those, especially useful in proof questions.